Hello and good evening. This is a project presentation for Cloud Computing CSE 416, and the topic Akshay and I have chosen is performance analysis of multi-threaded against single-threaded programs on a cloud environment. Right? So let's get right into it. The certain parts of this presentation that we want you to understand. First is the theoretical aspect, as in why multi-threading came into account in the first place. Secondly, of how it is useful in the cloud environment and why particularly in a cloud environment would we rather want parallelization of tasks rather than serial. Third, we're going to compare certain programs and going to show you outputs and give you live demonstration as to how certain algorithms or programs perform in terms of user time and whether it's always beneficial for you to, in a cloud environment, to have a multi-threaded system over a normal single-threaded system. So let's get right into it, right? So firstly, let's understand what is the history of multiprocessors. 15 years ago, IBM unveiled the world's first multiprocessor, the IBM 100, which had a clock speed of 1 gigahertz and a VLSI chip that contained 64-bit microprocessors and 170 million transistors. Since then, microprocessors have always grown in the number of transistors that they have and have become smaller in size. This is accurately reflected by the Moore's law. What does Moore's law state? Moore's law states that the number of transistors that are incorporated in a chip will double every 24 months. That is, you're going to have double the number of transistors that you had in the previous 24 months. Moore's law performed even better than its prediction, and the rate doubled every 18 months. After that, now we've come to such a point, and we're going to explain to you why we've come to such a point where we cannot have any more cores on our chip, right? So with the increase in the number of transistors on a chip, the amount of power that those chips consumed also increased exponentially, as you can clearly see from this graph, right? As the number of the performance of the transistors became larger, the amount of power that they consume also became larger. This means that if you had to fit n number of processors on a chip, this would grow exponentially, and this was not feasible at all, right? So what was our answer to power consumption and why multi-core chips came into being, right? Because if we incorporated more and more transistors on the same chip, this meant that you cannot deliver the same power. So what does this mean? This means that the software development was limited or hindered by the inability of hardware to play catch up with them. That means the software developers did not have a leeway to bring unoptimized code on systems that were running previous machines. That means that they had to change the way they had to code and make sure that the code runs on those inefficient machines that were existent previously. Also, what happened now was that new methods of integrating hardware had to come into picture, right? Because program requirement or the needs of the computers became exponentially large in terms of, if you talk about research purposes or if you talk about industrial applications, you needed strong computers. But how do you deliver them? Right. Instead of having a single multi-frame system such as the one that IBM had, what these companies did is to make sure that they have a group of inexpensive computers that could share each other's processing power, and the time that they take to solve a task simultaneously is reduced than the one that was used on a mainframe system. This is how multiprocessing came into being, right? Now let's talk about cloud and its applications, right? So we all know the benefits of cloud, that there is no upfront cost, there is zero maintenance, and there is horizontal scalability whenever you want at a single click, right? That means that you can have storage spaces, you can have loose service guarantees, and you can also use your space effectively and cheaply, right? That means that Amazon Web Services, Microsoft Azure, or like FutureGrid or OpenStack, or all these places could give you these requirements of hardware and software anytime you needed them, and you did not have to pay an upfront cost. So as it was more expensive to have these in-house computers, people started using cloud technologies to make sure that their computing needs were met in a proper manner. Right? So let's look at scalable parallel computing on clouds. That means that you can have various programming models. There is scalability. That means in a matter of seconds, you can scale your operations from a small growth to extremely large servers, and that can all be done online in a click of a button. The performance of cloud online is extremely important, and this is the area of our interest of what we're going to evaluate today. Right? You can monitor your progress, and you can monitor how much you pay, depends on how much you use. There's also a certain amount of fault tolerance that is available on the cloud, right? So let's look at the parallel frameworks and how cloud computing actually makes use of parallelization, right? So one example I'm going to give you that's extremely important over here is the MapReduce of Amazon Web Service. So I'm going to give you an example of how MapReduce works, right? So what does MapReduce do? MapReduce breaks a program into n number of components. All these components could be executed parallelly while the code within these components executing sequentially. That means that if n components took m amount of time, now each component, now to execute the entire program, you only needed m by n amount of time. That is to say that your job now is reduced significantly and programs are performing much better than they would have on a single threaded system. Right? So what are the profits of executing multi-threaded processes on a cloud platform? Firstly, it improves throughput. As that means that when you have a cloud computing platform and you're a cloud service provider, you have to yourself keep into mind that your systems are better utilized in a manner that you A, earn more profits, B, your systems are used to a minimum and they're used efficiently. What does this mean? This means that if you can parallelize the amount of tasks, that means you do not have to have multiple systems performing different tasks, but you can reduce those tasks to a limited number of systems that can perform them simultaneously. Right? So it improves throughput. Secondly, the response type of a program is improved. That means that if your data center or your cloud program center is too busy and you have multiple requests flowing in at every moment, if you can parallelize the amount of tasks, so the amount of time you need to service a request is reduced, and that means that the time taken for you to service the next request is also reduced. So the response time for a task is in effect reduced. Third, the server responsiveness is improved because the task is not blocked by any larger task that is there before you. And lastly, fault tolerance is improved. But all these advantages also come at certain costs. Now, what are the pitfalls of multi-threaded programs? Firstly, multi-threaded program is only profitable if the person implementing is a capable programmer. That means that he knows where to split the program or make sure that where the program is necessarily divided into parts that would lead to a best result. Secondly, multi-threaded processes happen on different threads simultaneously. That means that you can never guess if one thread fails, the entire program does fail and you waste the amount of time of implementing that thread. Third, if threads also undergo a parallel execution, then you are not very sure of where your program is executing. Fourth, debugging is totally based on intuition and trial and error because you do not know where your program might result into error. Another set of pitfalls is first the partitioning. It is extremely difficult to find a method or a part of a program in which could be executed serially altogether. Because the programs are becoming so complex and so intertwined with one another, most of the time the result of the one is the input of the another. That means that it is difficult to find a task that is happening in a sequential manner only, and it is difficult to then partition these tasks. Secondly, communication. So you need to identify where the communication pattern amongst the different tasks happen, and that is something of a pitfall. Thirdly, about mapping, of how you map these tasks to processing units, and that becomes an internal struggle within the architecture of where do you map these tasks and how do you best do them. Fourthly and lastly, agglomeration is to reduce the internal partitions to coarse grain tasks according to resources available. That means you have to reduce the internal number of partitions to fit in or accommodate more tasks, which has to happen on a dynamical basis, otherwise it does not work out.
When we talk about optimization in cloud, we need to realize why did we start using cloud in the first place. So we started using cloud to minimize the crashing of websites or the online websites we visit. What earlier used to happen was when we're using the websites, all the data is stored locally on some server, but when it's via cloud, all the metadata is stored on the edges of the cloud, and when you're visiting the websites again and again, it doesn't have to actually go to the server every time of the website to get retrieve data. It directly fetches it from the edges itself, from the edges of the cloud. That reduces the uptime, that reduces the downtime of the website, which increases the performance and reliability and performance of every website and everything on the internet. So this is why we started using cloud. Now it'll be more and more efficient as we make it more optimized. We need to make it optimize it as much as possible so as to reduce the stress and increase the performance, because of which we started in the first place. Now we use different algorithms to optimize this. Stop.
What is our objective here? Our objective is to focus and to answer certain questions. The first question being, does the division of a process into n number of smaller processes and executing them simultaneously make any significant change to the execution time of the process? Secondly, is the execution time difference so big that we need to get into the intricacies of the programs, because these also do not come without time? To optimize a program, you also need to spend a certain amount of time. What we are getting into is it worth doing all these tasks? So our methodology is as follows. Firstly, we're going to take a problem, we're going to put it through a serial execution, then a parallel execution, then calculate execution times of both, and then compare and analyze results, and we're going to give you a tabulated amount of results of which program was better and why it was so. This all we're going to establish and use OpenMP to get our results, which is incredibly important tool in cloud computing to set benchmark in a parallelized manner. This is the tool that we've used to calculate our running time, etc. today. So these are the characteristics of OpenMP, right? It's unarguably the most used language. It has a great deal of support and extension. Parallelism is achieved through libraries, and thread shall be implemented in C++ format, right? So there are two types of memories that are here. One is the shared message and one is the memory passing method, right? All these technologies can be used, and OpenMP implements both of them, and we're gonna just check the execution time of certain programs. These are the list of sample programs that we're going to execute. Firstly, matrix multiplication. Secondly, quicksort. Thirdly, this is extremely difficult mathematical problem which is called the Mandelbrot plot, and I'm going to explain when I reach the program of what it does. Fourthly, Dijkstra's algorithm, molecular dynamics, fast Fourier transforms, and prime number programs, right? And then we're going to evaluate. So let's move on to the implementation part of our program and how implementation is done. For implementation part of the program, we necessarily need to use an open source tool. And now these are the programs that we're going to implement with our tools. And this is the first program that we're going to implement is the Mandelbrot plot. For the Mandelbrot plot, first we'll execute the program that we have coded to be in a first, and then we're going to take out the time it took for the Mandelbrot plot to get plotted, and now we put the function over here and just run it, right? So just a second, and we put it over here. Yes, so we put it over here, and then now we begin. So this is the result, right? The real time is the total time it took for the system to complete it. The user time is the time it took for the user to complete, and the system time was between the systems, the communication of different processes. The time that it took was the system time. So the real time in this case is 1 second and 157 milliseconds. User time is 0 seconds and 964 milliseconds, and the system time is 0.008 seconds. That means that the Mandelbrot time, the total time it took to plot the Mandelbrot graph was 1 second and 157 milliseconds, right? So now in this case, the next thing we're going to do is implement a serial code as well. So first let's look at what the Mandelbrot plot looks like. So the Mandelbrot plot is all these pixels that you see around you have been mathematically devised, and these have been done through a function. That means that every pixel had to be calculated, and now the pixel around them also have to be calculated. Next, moving on, we look at the sequential version of the Mandelbrot plot. Again, we copy the line that executes the Mandelbrot plot, sequential line, and then also the time taken for it to compute. So let's put that in. Let's run it. So as you can see, the real time is 0.359 seconds, user time is 0.256, and the system time is 0.008. This means that the sequential time of the program is extremely less than the parallelized version of the program, as you can see over here. That means that the sequential version of this program is far better than the parallelized version, at least in the Mandelbrot plot, right? We'll tabulate this when we go to results. The next program that we're going to execute is the Fourier series program. Now in the Fourier series program, let's go ahead and copy the Fourier series program. Copy that in, go to terminal, paste it, then paste the time function that calculates the amount of time it took for the Fourier series to calculate. Yeah, here it is. Paste that in, press enter. Alright, so now as you can see, Fourier series is a never-ending function, and there is a point of time that the processor will kill the program because it cannot compute it, or it will take so much of time. So now we'll have to wait for that point where it kills it. Just a couple of seconds more. Yes, so now you can see it is killed, and it was killed over here, and the real time is 3 minutes and 55 seconds, 0.347 milliseconds. User time is 47 seconds and 0.86 seconds. The system time is 3 seconds and 208 milliseconds. This is the time that we took to execute the Fourier series. So it's now time to tabulate the results and verify of what we saw happening in programs that we executed, right? For the first program, that is the matrix multiplication, when we took a data set of 200 by 200, the sequential execution resulted in 1.44 milliseconds, parallel 1.13, and parallel four threads 1.04. So as we increase the data set, we similarly see that a parallel execution of matrix multiplication is much better than a sequential execution. This could be characterized by the graphs over here, which I've plotted, and this shows the parallel execution in 4 threads, this shows the parallel execution through 2 threads, and this shows the sequential execution. We notice that as the data set increases, or as the matrix size increases, parallel execution is cheaper than sequential execution, at least for matrix multiplication, right? So the conclusion of matrix multiplication is there is no dependency among the steps, because every step can be individually calculated, and the graph implies that this can be implemented in a better manner when we use parallelization rather than a sequential approach. But is this true for all programs? So let's move on. For Quicksort, we see So now in Quicksort we see that parallel execution reduces the time of execution drastically, like we saw in the matrix multiplication problem. As we increase the size of the data set, also the amount of time it takes to sort them reduces when they are parallelized. But this always baffles me, right? Because isn't Quicksort supposed to be faster when a sequential execution is included? But why is this the case? This is the case because Quicksort is always a program that relies on iterative processes. That means that the next iteration involves processes that have to be solved in the previous iteration. But in this case, data was manipulated to such a point that this did not make much of a difference. That means the iterative process that would have made difference in the other scenarios weren't as big a factor in the Quicksort case, and hence parallelization could still be applicable over here, right? This is the application that we saw for Dijkstra's algorithm. This is the application we saw for Dijkstra's algorithm. For Dijkstra's algorithm, surprisingly, we noticed that it is the multi-threaded that takes more amount of execution time than a single-threaded machine, right? Why is this the case? Because Dijkstra's algorithm is often most iterative process. That means that the next iteration of Dijkstra's algorithm has to be dependent upon the previous iteration, and the time difference in getting the result of one iteration from a different core to another iteration outweighs the time it would have taken if all executions were done on a single core, and hence Dijkstra's algorithm is more expensive on a multi-threaded system. Now in case of the Mandelbrot plot, we saw the multi-threaded systems required more amount of time than a single-threaded systems. Why is this the case? Because the Mandelbrot plot, when it has to populate each and every pixel, it also has to calculate the amount of pixels that are around it. That means that till the time the pixels around it aren't calculated, it cannot calculate that pixel. That means a lot of time the processor has to necessarily wait for the result from another multi-core or another core. That means that if this were on a single machine, this would have performed much better than a multi-threaded system. For Fourier series also, we know that fast Fourier transform is in which we require immense amounts of integration. Since the amount of integration done is over a curve and each segment of the curve is individually evaluated and you have to have the previous result in order to get the next result, you have to wait longer in a multi-threaded system like we are waiting longer over here in the fast Fourier transform. So this is the graph for prime numbers. In prime numbers, this is a very sequential process because you do not have to wait for anything. That means that if you have n series of prime numbers and those prime numbers have to be sorted in a particular manner, that can be done on different cores without the loss of execution of any time whatsoever, and hence a single threaded machine would perform worse than a multi-threaded machine in terms of prime numbers. Molecular dynamics program. In a molecular dynamics program, we saw similarly a single machine took more time than a multi-thread machine because the data could be divided in an efficient manner over the number of cores that were present. So what is the conclusion that we came to today? Firstly, that parallelizing serial calculation in OpenMP drastically reduces the amount of time it takes in multi-thread systems. Secondly, there is an extreme amount of computational speed up when parallelizing a serial calculation. Thirdly, the parallel calculation is twice as quicker than the consecutive speed up is linear, right? Also, cloud technologies work extremely well for parallel applications, but not all amount of parallel applications can be used on a cloud technology. What does this mean? This means that if you're loaning out your cloud to a particular scientist or a particular university, that means that they have to have more amount of serial calculations involved in the processes. Because more importantly, of all scientific processes use a certain amount of iterations within them. That means that if you spread those iterations over n number of cores, doesn't mean that you're going to reduce the computational time of that program. So you have to be wise about where you use what technology for your cloud to make sure that you are the best possible placed to make more profits. Thirdly, applications sensitive to latencies experience higher overheads, right? Also, in-node communication support is crucial because you have to have the minimum amount of time between multiple cores and them talking to each other and getting the data from one another, right? So lastly, parallel computing helps save a lot of time of computation and solve larger problems. To use parallel programming, we need to have a parallel programming model and a program that could be broken down into certain segments and improve the time. Thirdly and lastly, performance of parallel computing is measured with speed up and efficiency. So as we saw, not all programs can be parallelized, but not also all linear programs perform worse when parallelized. In fact, the opposite is true. Most of the time, parallelization would lead to a better outcome, and we have to evaluate and certainly put a cloud to use in such a manner that it optimizes the use of all resources. With this, we come to the end of this presentation. We hope that you learned something from it, and we hope to see you next time. Thank you.